Welcome to EE228, Continuous Time Signals and Systems. In this first video in the course, a video on continuous time signals. Before we begin, I'd like to acknowledge the folks who have contributed to this video and the presentation that's inside. This video is presented to you by Dr. Wayne Pilkington, with contributions from Dr. Clay McKell and Dr. Fred DePiero. Also references information from the textbook Signals and Systems by Dr. Mahmood Navi, and Analog and Digital Signal Processing textbook by Ashok Amardar. In this video, we'll cover what is a signal and look at some examples and some different forms of signals. And then we'll talk about how we classify signals based on their determinism, their amplitude characteristics, their time characteristics and periodicity, whether they are power or energy signals, and different symmetries that may appear in their wave shapes. So what is a signal? Before I give you the answer, think about that for a moment. How would you describe what is a signal if someone didn't know? What would you tell them is important about a signal and what it actually is and what it's for? When we think of signals in electrical engineering, we think of different waveforms, things we see in an oscilloscope, things we draw out in a paper, things we describe mathematically. And generally, we're talking about time-varying waveforms. They're not interesting if they're just a straight line. This time-varying waveform generally represents some variation in time of some sort of physical phenomena, whether that's air pressure, an electric field, some vibration, some economic indicators. For us as electrical engineers, we're used to signals in the forms of voltages and currents. But there are many, many other physical forms of signals in different shapes that they may have that are of interest to us. One of the most important things about signals is that they represent some sort of information. That could be data, that could be messages, it could be commands, it could be the status of something, it could be music that we want to listen to, different important measurements we want to make, or just warnings of something bad that's going to happen. These are all forms of signals. The way they capture that signal is usually encoded in some part of the waveform, some part of the signal itself, something that's measurable that we can pull out from it, and something that we can have some control over varying. That could be, for example, the shape of the signal itself, or some pattern that appears in the signal. It could be some characteristics of the amplitude or the changes in amplitude, as in amplitude modulated AM radio. It could be the frequency of the signal that carries the information, or the change in the frequency, as in frequency modulated communications. It could be the time, position, or phase of information in some pattern, as in some digital encoding schemes. It could be the duty cycle of a waveform in terms of something like a pulse width modulated waveform. As long as we have some aspect of the signal that we can manipulate and vary in a way that's measurable, we can encode information and extract it from that signal. Signals inherently transfer that information from one point to another, from what we call the source to the receiver. What form the particular signal takes, its physical form, depends on what medium it's being conveyed in. Again, we're used to electrical signals. Voltages and currents are our favorite kind of signal, usually happening and being conducted through copper wires. Similarly, electromagnetic waves are an important form of signal for us. Those could be radio waves, cellular signals for our phone systems, Wi-Fi signals for our computers, Bluetooth, even radar and X-ray kinds of systems and signals. These are generally conveyed over the airwaves. Another kind of signal that passes through the air are sound waves, which are actually just acoustic pressure waves moving through space. Now, if that's audible sound, that could be things like music and speech that is carried through the air that way, but at frequencies that we can't hear with our ears, like ultrasound signals or sonar signals, are also forms of acoustic pressure waves. Mechanical vibrations could be a form of a signal, or the position of a mechanical object as it vibrates could be plotted as a signal. Light is another way that we convey signals from one point to another, whether that's through a fiber optic cable, or over the airwaves using lasers, or even out into space. For example, we have now optical communication systems that might use light to convey digital information. And of course, there's a whole host of other forms that signals can take, whether they're in an environmental context, a biological context, a chemical system, a physiological system, a societal system, and so on and so on. So there are so many different kinds of signals that we encounter every day. What we want to do today is come up with different ways to classify signals, to hone in on what kind we're talking about and what their particular characteristics of interest are to us. And for that, we'll be trying to parse signals into these various categories that you see here. Rather than naming them now, let's push forward into seeing what these are. The first way we'll distinguish signals is whether or not they're deterministic. As the name implies, a deterministic signal is one that we can predict in advance without any error. We can predict its value at any particular instant in time by knowing its essential characteristics. Usually these would be waveforms that are expressed in terms of some mathematical quantities or functions or shown on a graph, and that we can use those mathematical functions to predict at any particular instant in time what will the value of the function be. That's as opposed to a random signal where we really cannot know with certainty exactly what the signal value is going to be at any particular instant in time. Our model doesn't tell us precisely what it's going to be. Usually these are characterized more by statistical measures. What's the mean value of the signal? What's its variance? Or if we want to know its value at any particular time, all we can talk about is probabilities. What the probability distribution is for the signal value at a particular instance. For this course for EE228, we're going to deal entirely with deterministic signals. These are ones that we can describe with mathematical quantities, we can draw on or see on an oscilloscope, not ones that are particularly random in nature. Now, sometimes we will use this as a simplification. We'll talk about or try to model systems that may actually have some randomness to it, but we'll be assuming that for our purposes they are deterministic and that random element is really not affecting things very much. Now, if you're going on an EE curriculum, there will be other places where you'll be addressing random signals. For example, in communication systems, it's very important to analyze and look at signals and their randomness. And you'll be preparing for that by taking a statistics course to be ready to address those issues. But for now, we're going to stick to the world of deterministic signals. Another distinction we can make between signals, and this is important for this particular course, is whether or not they're a continuous time signal or a discrete time signal. Here's a picture of a continuous time signal, usually denoted as x of t, so a function of time. It's a time-varying signal. We use the subscript c to say that this is in fact a continuous time signal, and this signal is a continuous function of time, meaning that it has some value at all instances of time t, and we can parse our time index to whatever level we want, however many decimal places we want, and be able to, at that particular instant in time, be able to pick out a particular amplitude value for our waveform. That's as opposed to a discrete time system, which often comes from sampling a continuous time signal at certain instances and creates a sequence of numeric values that represent those sample values. Now, this we say is a function of discrete time because we only have information about this signal at particular instances in time and know nothing about the signal in between those time instances. So it's defined only at these particular instances, these discrete instances of time. Typically, these instances occur at integer multiples of some sampling interval, where t sub s, shown here, is the sampling interval, the time between two samples. And our discrete time signal, then, is a sampled version of the continuous time signal, and we find it by evaluating the continuous time's function at particular values of time, t, that are integer multiples, n, times that sampling interval, t sub s. Once I do that sampling, I have a collection of discrete time values, and I'll express them not in terms of necessarily time, but as their sample index using this integer index n. Again, the distinction here is that at those particular instances of time, I know exactly what my signal value is. But for any time in between, I have no information. I don't know what the signal value is. It could be anything. This course will deal exclusively with those continuous time signals. We'll be using continuous time functions, continuous time transforms, continuous time differential equation solutions to find and analyze our signals and systems. That's as opposed to the follow-on course, EE228, that deals with the discrete time world and repeats these kinds of analyses, but using now the new limitations that come into play when we sample signals and only have these particular discrete time values for them. Taking this a step further, we can delineate between more familiar names of analog and digital signals. Analog signals are generally continuous time signals. So they are again defined at any value of t, but they also tend to be continuous functions of amplitude as well. So their value, their level at any instant in time is also a continuous function. Think of it as we could express its amplitude using a floating point number with multiple decimal places. That's as opposed to digital signals that tend to be first discrete time signals, so they're only defined at discrete instances of time, but their amplitude is also quantized, just as their time instances are quantized. In this case, digital signals are quantized into a finite number of allowable levels, the most basic form of which is a binary signal, where there's only two values allowed, 1 or 0. If we have a more general sampled data signal, we might have a digital signal where we've taken an analog signal and sampled it, but we would also have to quantize it in general, so that its amplitude level must conform with one of only a finite number of available levels. Usually these levels would be expressed with numeric values, and those numeric values might be represented using integers. So while the analog signal has many decimal places in its voltage, for example, a discrete time signal would have to be rounded to the nearest integer value. So analog signals are continuous both in amplitude and in time. Digital signals, strictly speaking, are discrete both in the time axis and in the amplitude axis. Taking a continuous time signal, we can also look at the amplitude of the signal and divide signals into two different types again: a bounded signal and an unbounded signal. As the name implies, a bounded signal is one where I can define some level m that bounds this signal, meaning that for all time t, the absolute value of that function x of t has to stay within the boundaries of m. Its absolute value must remain less than m. Its actual value must remain between plus and minus m for all time, not allowed to exceed m in either direction. If it does exceed and goes off to infinity, then it's an unbounded signal. Now, a signal is bounded as long as I can define some finite value m that bounds that system. It could be a huge value. It could be 10 million. But as long as it bounds an upper bounds for that signal, we would consider it a bounded signal. Only if the signal goes off to infinity is it unbounded. We can also look at the boundaries in the time axis as well, and delineate between a finite length signal, which we'll also call a time limited signal. In this case, we'll give it that name, time limited or finite length, if the function x of t goes to 0 for all t less than some value alpha and all t greater than some value beta. If it's infinite length, it never quite goes to 0, never settles down, and just continues to go on and on and on at non-zero values in both directions. Now, between these two extremes, there's some other subtle combinations that we'll distinguish. First, a signal could be right-sided or left-sided, meaning that it's closed down on one side and either open or finite on the other. Here are two examples of right-sided signals. In both cases, the point is on the left side of the signal, it goes to 0. Said mathematically, a signal is right-sided if the signal x of t has to be 0 for all t less than some value alpha. Now, alpha can be a positive value as shown in the top, or a negative value. That doesn't change whether it's right-sided or not, just that it's closed off on the left side, goes to 0 on the left. It's left-sided if the opposite is true, if it goes to 0 and stays that way for all values to the right. Or mathematically, if x of t is 0 for all t greater than some value alpha. Again, doesn't matter if alpha is positive or negative, as long as it goes to 0 and stays that for all subsequent values of time, then it's left-sided. So a signal can be right-sided or left-sided. Now, a special case of a right-sided signal is one like the top, and that's a causal signal. Causality is a very important concept that we're going to keep coming back to over and over again, so we want to be very clear about this definition. We consider a signal causal if it's right-sided, for one, but the important concept is that for all values of time, t, less than 0, a causal function must have an amplitude value of 0. So it has to be completely zero for all negative values of time. At the top we have a causal signal. Now that signal can go to zero again on the right. That's fine. That doesn't change whether it's causal or not. What's important is that all values for the function have to be zero for all values of time prior to t equals to 0. If we look at this lower function, then this one happens to be right-sided but not causal. We would call this a non-causal signal because there are some values of time less than 0 where this function x of t has a value other than 0. Now there is an opposite to a causal signal, and that's shown here in the upper right. This would be an anti-causal signal. Here the opposite criteria apply. X of t has to be 0 for all t greater than 0. So like a backwards causal signal. So this signal at the top right is left-sided and anti-causal. Looking at the lower right, this left-sided signal is neither anti-causal nor causal. We would just call this one non-causal. We don't usually use the terminology non-anti-causal. Now, another important distinction of signal types is whether or not they're periodic. You know now that periodic signals are ones where we could recognize by sight as having some pattern or some shape that keeps repeating on and on and on. And in our case, we want patterns that repeat exactly, so they're unchanging from one period to the next. The mathematical definition and test for a periodic signal is that signal is periodic if I get a function value x of t, and that function value repeats every time I advance the time argument by some integer number times the period of the signal, where the period is capital T is shown here. The period is the time for one cycle of the repeating pattern, and so x of t has to be the same as x of t plus n times capital T, where capital T is the period and is any integer, positive or negative. If we take the reciprocal of the period t, that defines what we call the fundamental frequency. That is 1 over capital T then. In general, we assume our periodic signals to be truly periodic are infinite duration. They're not time limited. If we want to be absolutely certain to denote that, we can use this 3-dot notation, showing that the signal goes on and on and on in both directions with the same pattern. So periodic signals are ones where we have some pattern that keeps repeating over and over again. The converse of that would be a non-periodic, or also called an aperiodic signal. Here there is no one shape, no one pattern that keeps repeating over and over again. That's not to say that there aren't some values that happen more than once, or some short segments that may look like they repeat again and again, but we don't have the exact same pattern repeating over and over again constantly in both directions. Now, in electrical engineering, we also delineate between two kinds of signals, calling them either power signals or energy signals. Before we get to how we delineate those two, let's do a quick review of what we mean by power and energy. Particularly power, there are a number of different expressions for power, and we have to be very clear about which ones we're talking about here. When we first think about power, or we're first introduced to it, we're introduced to the idea of instantaneous signal power. So if we had, for example, a time-varying current going through a resistive load, we would develop a time-varying voltage across that resistance, and they'd be proportional by the resistance value. If we use P as our power indicator, and if it is a time-varying excitation, power will be a function of time, at least the instantaneous power will be. And in this simple circuit, it would be V times I, which, because of their relationship through the resistance R, we could express as either V squared over R or I squared R. And if the voltage changes with time, so does the power. If the current changes with time, so does the power as well. Now, when we're talking about signals and the power and signals, or the energy in signals, we usually use the normalization of assuming that that signal is driving a 1 ohm load. And so then the power is proportional to the voltage squared or the current squared. Since it's either of those, we can use the same variable x of t to represent either a voltage or a current. So if the signal has a value of x of t, the power in the signal is x squared of t, again assuming that the resistance is 1 ohm. Now that's the instantaneous power. Again, it's a function of time, and we show that explicitly with the function arguments. When we're talking about the energy in a signal, we're usually talking about the total signal energy. That's the integral of the instantaneous power over all time. And so we could take the instantaneous power, p sub I of t, integrate it over all time, and that would give us the signal energy. That would also be the same as the integral of x squared of t. Again, x could be either a voltage or a current. Now notice in this expression we have some absolute value signs showing up. What's that all about? Well, that's only covering the case if our signal happens to not be a real valued function. If it happens to be a complex function, then we want to do this integral over the magnitude of the square root of the function. So here's an example. We have a continuous time signal shown here of x of t. If I wanted to know what is the instantaneous power in the signal and what is the energy in the signal, first we would take x of t and square it and get the x squared of t function, which, because we started with a real valued function, that's the same as the magnitude of x squared of t. So we plot that versus time. The plot itself, the envelope of it, is the measurement of the instantaneous power at any instant in time. Again, a time-varying function. It changes its value as the signal changes. The total signal energy, therefore, would be the total area under that curve, under that instantaneous power curve. So we would integrate that whole blue area to come up with the signal energy. The signal energy would be a single value, not a time-varying function. It would be one value for this entire signal, whereas instantaneous power would be a function that changes with time. When we talk about signal power, we're usually not talking about the instantaneous power, but the average signal power. The average signal power is, as the name implies, a time average of those instantaneous power values. And look at that over the entire extent of the signal. Another way of expressing that is it's the total signal energy divided by the time over which we're doing that integration, an energy per unit of time. Thus, our familiar unit for power, watts, is joules per second, energy per time. In integral form, then, we can integrate the instantaneous power, which is x squared of t, over some interval, minus tau over 2 to plus tau over 2, and divide it by the time duration tau, by multiplying by 1 over tau. And if we want to cover the entire signal, we would have to let tau go to infinity in both directions. This would be the expression we would use particularly for a non-periodic signal. For a periodic signal, the average instantaneous power value is the same for one period as for 2 periods, as for 3 periods, as for an infinite number of periods. So to get the average signal power for the entire signal, we only have to integrate over one period. So we would do the integral of the x squared of t from some starting point to some starting point plus one period. Take that integral, that total energy, and divide it by the period, capital T. And that would be the average signal power then in that periodic signal. So here's a simple sine wave with an amplitude of A. And if we wanted to know what is the average signal power in this waveform, we would square it, which would bring all the negatives to positive as well. And we could integrate over one of those periods to find the signal energy and divide it by a period to get the average of the instantaneous power over all time, which is the same as the average of the instantaneous power values in one period, or the energy in one period divided by the time in one period. Now, how do we use this to distinguish two kinds of signals? Well, here's our first example again. This particular signal, if we take our x of t and square it, we know again the envelope is the instantaneous power and the area under that envelope is the total signal energy. This particular signal, if we wanted to find the signal power of it, we'd have to average the instantaneous power but over all time. Another way of saying that is we'd be totaling up the signal energy in this little finite block that we have, but dividing it by the whole time that the signal might have existed, which is time going off to infinity. So this particular signal, because it's time limited and has a finite duration, it's certainly not periodic. It has a finite amount of signal energy, the area under that x squared curve. But when we disperse that finite energy over all time to get an average signal power level, we get 0, because we take that finite energy level and divide it by an infinite time. So for this particular signal, it doesn't really make sense to talk about its signal power. it's more relevant to talk about how much energy is there underneath that x squared curve. And so we refer to this kind of signal as an energy signal, because energy is the appropriate quantity to describe it. That's as opposed to our periodic sine wave kind of signal, where again, if we square it and look at the total energy under that squared sinusoidal signal and take an average of the instantaneous power values, we get one value for the average signal power. This particular signal is not time limited. It has an infinite time duration. It is periodic. And because of that, it has infinite total energy. The total area under that x squared curve is infinite. However, it has a finite and non-zero signal power, the energy per period. And so for this signal, it doesn't make sense to talk about its energy. Its energy is infinite. It does make sense, however, to talk about its average signal power. And so we would call this a power signal. Now, as these examples imply, typically power signals are our periodic signals, and our energy signals are the more finite length ones. In addition to these characteristics, signals may also have certain symmetries. These terms, again, may be familiar to you, but just to review them in a signal context, we can talk about a signal having even symmetry, or odd symmetry, or no symmetry. An even symmetric signal is one where it looks like a mirror image of itself around the t equals 0 axis. So mathematically, a signal has even symmetry if for all values of time t, x of t is exactly the same as x of minus t. So if I find the value of the function at x of 3 seconds, I'll have the same amplitude in my signal at x of minus 3 seconds. Odd symmetric signals, on the other hand, look differently. They look like both a mirror image in the time axis and in the amplitude axis. So it's like we took the signal and flipped it around the origin. In this case, mathematically, x of time t is equal to the negative of x of minus t. And for this to be true for all values of t, they have to converge at t equals 0. So x of 0 must have a value of 0 for an odd symmetric signal. Now again, these symmetries are always with regard to the t equals 0 axis. So it's even symmetric around t equals 0 or odd symmetric around t equals 0. If we shift these waveforms over, they'll no longer be officially even or odd symmetric around the 0 point. Now some other familiar examples of even and odd symmetric signals. Cosine waves are a very familiar even symmetric signal, and sine waves are a very familiar odd symmetric signal. An interesting consequence of even and odd symmetry and how they work together is that any function, f of t, whether it has even or odd symmetry itself, can be recreated from a different even symmetric signal and odd symmetric signal that were derived from that original signal. Said another way, any function f of t can be represented by the sum of an even symmetric function we'll call f sub e of t, and an odd symmetric function we'll call f o of t. F of t can be reconstructed from the sum of those two, of an even signal and an odd symmetric signal, as long as we determine that even symmetric and that odd symmetric signal with this specific formula. The even symmetric signal will take the original function f of t, add to it a time-reversed version of f of t, and divide that sum by 2. For the odd symmetric part, we'll take the original signal f of t and subtract a time-reversed version of the signal f of minus t, and take half of that. If we create fe of t and fo of t using these formulas, we can add those functions together and get back f of t. Now you can see that that works mathematically by looking at these expressions. We could also see it graphically. Here's an example of an arbitrary function, x of t. If I want to know what is x of minus t, I basically flip that around the t equals 0 axis and run it backwards. Now our even symmetric signal we wanted to create from this says to add up those two signals to each other and cut their amplitudes by 1/2. And so we get this trapezoidal shaped signal that has an amplitude of 1/2 instead of 1. That goes from -2 to +2. The odd symmetric signal would be subtracting off from the original signal a time-reversed version of it. So now the x of minus t signal is flipped upside down, in the negative amplitude direction, added to the original x of t signal, and both scaled by 1/2. Now if we want to recreate x of t, all I have to do is add my odd and even versions, xe of t and xo of t together, and hopefully you can see visually that we get back the original signal that we started with. One other important kind of symmetry that you may not be familiar with, and that's going to have consequences for us in a number of our analyses, is whether or not a signal has half-wave symmetry. Now this really only applies to periodic signals. So a signal has to first meet the periodicity requirement that x of t is the same as x of t plus n times capital T, where capital T is the period. In this case, we're not comparing for half-wave symmetry a function and its value one full period ahead, but a function and its value 1/2 of a period ahead. If a signal is half-wave symmetric, I should be able to look anywhere on my signal x of t, choose any starting point, advance by 1/2 of its period, and the value of the function 1/2 a period ahead of where I started has to be the negative of the value that I started at, or vice versa. So mathematically, x of t equals the negative of x of t plus capital T over 2, where capital T again is a full period. If the waveform meets that requirement at all points in one period, then it is a half-wave symmetric waveform. So we've seen how to classify signals, whether they're deterministic or random, continuous time or discrete time, analog or digital, bounded or unbounded, time-limited or infinite length, right-sided or left-sided, causal, non-causal, or anti-causal, periodic versus aperiodic, and then finally looking at these symmetries: even symmetry, odd symmetry, half-wave symmetry, or no symmetry. Well, let's try out our understanding here. Here's a signal. Think to yourself, is this a deterministic or a random signal? Well, we want to look at the waveform, and we seem to have a pattern that repeats again and again and again, and exactly the same at all times that it repeats. And so this one, because it's not changing, we would call deterministic. Continuous time or discrete time? Well, that's easy. There's not samples, so definitely continuous time. Bounded or unbounded? Well, you can see very easily, definitely bounded. Time limited or infinite duration? Well, we don't have all values shown here, but it certainly appears like this signal goes on and on. If we again wanted to be explicit about that, we could have added our 3 dots to each side, pardon my dots, to let us know for sure that this is going on and on in both directions. That was omitted here, but I think we would assume this one was in fact an infinite duration signal, repeating on and on. And not only that, but periodic. Again, we have the exact same pattern, repeating with exactly the same frequency, exactly the same amplitudes, so definitely periodic. Is this causal or non-causal? Well, here's our t equals 0 point. So we look back here and see that, yes, we have values other than 0 in our waveform, so definitely non-causal. And finally, does this have any symmetry around t equals 0? Even, odd, half wave, or none? Again, looking around t equals 0, we see what looks like this might in fact have even symmetry. We have the exact same values on each side, repeating over and over again, and so definitely not odd. Looks like it might be even symmetric. And then we look at one period here. This looks like one period between here and there. There's our capital T. And so if we were to go to half a period, here's our t over 2. We definitely don't have the negative of our starting point when we go ahead by half of a cycle, so definitely not half wave. And since we have some symmetry, it's definitely not asymmetric. So this would be simply an even symmetric signal. Now notice it is possible for a signal to have more than one symmetry. It's possible to be half-wave symmetric and even symmetric, or half-wave symmetric and odd symmetric. It just can't be both even and odd at the same time. Hopefully that example was helpful. Here's another signal. Take a close look at this one. This is actually a real-world signal. Would you call this one deterministic or random? Well, it's certainly an odd shape. It would be difficult to describe mathematically, but it does have a distinctive pattern to it. Kind of looks like it might be a periodic signal, and it might be deterministic. So let's take a very close look at see whether or not that's true. If this is truly a periodic and deterministic signal, then I should be able to move ahead by one period and have exactly the same value everywhere. And I'm going to look really close at some of the details here. And we see while the basic pattern looks pretty similar, well, let's see our period of repeat. Looks like we go from here to here, and then from here to the next one. Looks like 1, 2, 3, 4 blocks plus 1. Yeah, looks like about the same period. We notice the tops here look a little raggedy and a little bit different here. And if we look at our amounts of overlap here and here and here, we see some subtle changes. So it turns out that these waveforms are mostly periodic and mostly deterministic, but there's a small randomness to them. There's a change going on from one instance to another. And so this is mostly deterministic, but it has a little bit of randomness to it as well. So this is a signal that doesn't quite fall exactly into one category or another. And that's the case with a lot of real-world signals, which is an important point for this course. A lot of the signals we want to analyze and look at, we will assume and treat them like they are deterministic. And we may assume and treat them like they're periodic. But the real-world signal may be a little bit more complicated than that. But we have to recognize that these assumptions are built in, that we've made some simplifications, that we've assumed the signal is deterministic, or we've assumed it's periodic, and that the real signal has some other nature to it that we haven't exactly modeled perfectly. And so there will be some error in our analysis, in our results. So we have to keep that in the back of our minds. Again, this signal looks mostly periodic. I think if we looked at enough instances, and since this is a real-world signal, this is actually an EKG signal, a heart rate monitor signal. And as you might imagine, your heart rate for over a short period of time is pretty consistent. But if something happens or you start exercising, that time period between heartbeats is going to get shorter as your heartbeat rises. And so looked at over a longer period of time, the periodicity of this signal won't be so exact. It will fall apart. So we might model this, though, still as a periodic signal, even though it's not exactly that, and recognize that, again, we're making an assumption. We're simplifying things for the purposes of being able to do some analyses with some reasonable amount of work and get to an answer that's useful, even if it's not exactly perfect. This particular signal is definitely not causal. If we define this as our time t equals 0 axis here, then we do have signal prior to that, so this would definitely be a non-causal signal. And in terms of symmetry, well, our little peak here looks kind of even symmetric around 0, but we don't have to go very far in the signal to see that it doesn't really have the same values either side of that. And so definitely not an even symmetric, not an odd symmetric, not even half-wave symmetric. So this would be an asymmetric kind of signal. With that concludes this introductory lecture on signals. Hopefully that was informative. Feel free to go back and review any parts that were not clear. Again, please reference the associated notes that go with this video, and we'll look forward to seeing you next time.